Swayam Prabha. Digital India. Educated India.
Welcome to another module of Introduction to Machine Learning. Today we will look at estimating the probability density of a given sample and then resampling from that sample to generate new samples. So the learning objectives are: we should be able to list the applications of density estimation and sampling. We should be able to estimate the sufficient statistics of some distributions, and we should be able to test the goodness of fit of certain distributions, and write the expectation maximization algorithm for mixture of Gaussians, and fit a kernel density estimator on a given set of samples, and also generate samples using Monte Carlo methods or Markov chain Monte Carlo methods from a given distribution. So the first question that comes to mind is, why estimate the density of a given set of samples? So let's say we are given a bunch of data points. So let's take a two-dimensional space for example. So let's say this is an x1 x2 space, and all we are given is some distribution or some set of samples here, right? So question is, why even try to estimate the density of the samples in this distribution? The first application that comes to mind is that we can perform basic statistical tests, such as what is the mean of the sample, what is the variance or covariance of the sample, what is the, if it is a single dimensional sample, right? So if it is only x1 and we are given bunch of points, then what is the standard deviation, what is the skew, what is the kurtosis, those kind of things, what is the minimum and the maximum, etc. The second question could be that, can we identify outliers? So let's say we are, most of the samples are here, but there is one sample here which here looks, visually looks like an outlier, but can we statistically show that it is an outlier? Then we want to use Bayesian methods. In those cases we may want to use a density estimation. So for example, if we are building a Bayesian classifier where we want to make a decision based on P of class 1 times P of x given class 1, right? So then this particular estimate could come from a probability density estimation, okay? And then finally generate new samples. So given a bunch of samples here, can we generate new samples for various reasons? We may want to augment the data, we may want to create an extra set of samples so that we have a larger samples to fit the data on. We may want to create new samples that do not violate the copyright of the existing samples but generate plausible new samples, for example deep fakes and so forth. So these are all good reasons for why we might want to generate samples from a given set of training samples. So the easiest way to do density estimation is to do parametric density estimation. What that means is, we assume that the underlying distribution is a distribution of a known kind with a certain set of parameters, and then all we need to do is estimate those parameters. So the complete way of looking at it would be that we would first visualize the data, then we will shortlist candidate distributions, then we will estimate the distribution parameters, and then we will check the fit or the likelihood of that distribution. So let's take an example. So let's say we are given a single variable, okay, and it is basically and these are the samples of the distribution, the crosses that I have marked. So, and we see that there is nothing outside of, on this side there is nothing outside on this side, and looks like there is no particular region here where the data is more dense versus less dense. So most likely this is going to be a uniform distribution. On the other hand, so what is the y axis here? Sorry, the y axis is going to be p of x if x axis is x. On the other hand, if we are given another set of samples and looks like there are several samples close to a particular value and then less and less samples as we go further away from that value, then most likely this is going to be a Gaussian distribution. So once we visualize the data, we know what are some candidate distributions. If we have a distribution that is skewed towards one side, then Gaussian may not be the right choice, even though we have so let's say there is nothing on this side, but like everything, so let's say we have a bunch of points here, but then they go sparser and sparser as I go towards the right, but there is nothing on the left. So this could be an exponential distribution, for example. So once we visualize the data, and this could be in multiple dimensions also, we get a sense for what are some of the candidate distributions for this particular data. So we shortlist those distributions, then we estimate the parameters of those distributions, which I will come to in a short bit, and then we will check, comparing two different distributions, which one is the better fit. There is no such thing as the optimal fit, there is only better fits and not so good fits. We can only compare distributions. So that is what we will look at shortly. So what is so how do we estimate the parameters of a distribution? One of the ways of doing that is to look at sufficient statistic. So what is sufficient statistic? Basically these are a set of numbers that if we find these set of numbers, these numbers will maximize the likelihood of fitting on the data of that particular family of distributions. So let's talk about a family of distributions. So let's say we are looking at Gaussian distributions, right? So the Gaussian distribution in one dimension is described by a mu and a sigma. Okay, so the mu is the center of the distribution, or the 50th percentile of the distribution, and sigma tells us how wide is the distribution. So for example, we could have a mu here, and then we could have a distribution like this, or we could have a mu somewhere else, and we could have a distribution like this. Both are Gaussian, but they have different mu's and sigmas. Okay. So there are certain distributions where you estimate, if you estimate certain statistics of those distributions, you will be able to find the parameters, the maximum likelihood parameters of those distributions. So let's look at what those statistics mean. So what is a statistic? First of all, it's a descriptor of the distribution. So examples of statistics could be the mean, the variance, okay, min, max, etc. So anytime you take the distribution and you reduce it to one number, that is a statistic of that number, okay, and that one number is a descriptor. So it could also be, let's say, min and max combined, it could be a range also. So if you reduce it to a few set of numbers, those are the statistics of that number. So this is, for example, expected value of x, this is expected value of x minus expected value of x whole squared, etc. Right. So and then you have the min and the max. So once we can find certain statistics of certain descriptors of certain family of distributions, then we will be able to find the maximum likelihood parameters that will best explain the data. So in this particular case, for example, you may have a mu1 and a sigma 1, and then you may have a mu2 and a sigma 2. So between these two, one of these will be a better choice for a given set of samples. Which one is a better choice? Let's see how we can find that. So as you know, the formula for Gaussian distribution is what is given here, and in high dimensional, in more than one dimension, it is given here, where the C is the covariance matrix, okay, and mu is a vector and x is also a vector. Here x is a scalar, mu is a scalar, and sigma is the variance of the data, and that is also a scalar. This is for one dimension, and this is the expected value of x is mu, and expected value of the square of difference from the mean is the variance. So here, how do we fit a Gaussian distribution? So basically, let's say we are given a bunch of points. So this is your axis, and we are given a bunch of points. Okay. So for this bunch of points, let's call them xi. All right. So there is something called a sample mean. So sample mean, let's call it mu hat, is going to be simply sum of xi divided by n. N is the total number of samples. So I runs from 1 to n. Okay, so that is a sample mean. This is sample mean. Similarly, we can have sample variance, and depending on whether you want a biased or an unbiased estimator of the variance, we will take xi minus mu hat. Okay. We will sum this over I, the square of this, we will sum it over I, and then we might divide it by n or n minus 1. Okay. Depending on whether we want the bias estimate or unbiased estimate. So that will basically be the sigma hat square. So it turns out that for a Gaussian distribution, basically when we want to find a maximum likelihood estimator, then what we simply do is we set mu to be mu hat, and we set sigma to be sigma hat. Okay. That's all we need to do. So basically we take the sample, and for the sample we compute the mean, sample mean, and assume that the Gaussian has the same mean, and for the sample we compute the variance, and we assume that the Gaussian also has the same variance. So what I will do is I will put a star here, because if I put a star, that means these are optimal in some sense. It's a notation that we often use by putting a star. And if we use any other mu2 and sigma 2, okay, the likelihood of the given data is going to be lower than if we use sigma star and mu star. Okay, so these are going to be optimal. Optimal in the sense of optimal for maximizing data likelihood. So these are something called sufficient statistic, that if we just estimate these statistic, we know pretty much everything about the distribution, and we know the best fitting distribution for the given data. So this idea of sufficient statistic is only applicable to certain types of distribution, not for every distribution. Some other examples where these are applicable is a Gaussian, is an exponential distribution. As you know, an exponential distribution is going to be 0 when x is less than 0, okay, and it is going to be lambda times e to the power minus lambda x if x is greater than or equal to 0. So it looks like either this or it looks like this, and so forth. And just to remind you, the area under all of these is going to be 1, because these are probability density functions. So here, if we just find the sample mean, which is expected value of x, if we just find mu hat, okay, what we can say is that lambda is equal to 1 over mu hat, that's it. So just finding the sample mean is a sufficient statistic, and that will give us a best possible estimate or maximum likelihood estimate for an exponential distribution. But here we have to first visualize and see that there is nothing here, there are no samples in the negative range. The samples are more concentrated towards 0 and sparsely concentrated as we go further away from 0. Only then it is a exponential distribution is a likely candidate. Out of all possible exponential distributions with different lambdas, the best fitting distribution is the one that that is given by this 1 by mu hat. Similarly, we can look at uniform distribution. If we see a bunch of sample points that are almost uniformly distributed between two extremes and there is nothing outside those extremes, then basically the uniform distribution itself is given by 1 over b minus a, where b is the upper limit and a is the lower limit, okay, and outside of that it is 0, else 0. Okay. So here the estimate for b and a is simply, for b it is going to be max over xi, and for a it is going to be min over ai. So if we perturb a and we make it slightly larger, we are going to miss the lowest, sorry, over xi. If we perturb a and we make it slightly larger than min of xi, then that min of xi will be 0 according to the distribution, and consequently with the IID assumption everything is going to be 0. So what is the likelihood of the data? So the likelihood of the data is product over I, okay, so whatever is the distribution f, or let us say whatever p theta of xi, okay, and the log likelihood is going to be sum over I log of p theta of xi. Okay. So what we want to do is we want to maximize either this or this, maximize. We want to find a theta, theta is the parameter. So theta is mu or sigma in case of Gaussian, it is lambda in case of exponential, it is a and b in case of uniform distribution. We want to find the theta that will maximize the product of all individual probabilities. Where this comes from is from the IID distribution, independently identically distributed. Independence leads to the product, identical leads to reuse of the same probability density function inside the product, and if we take log we will get the log likelihood. So this is what we want to maximize, and what we have looked at the sufficient statistics in the last 3 slides, these are the ones that will maximize the likelihood for this particular family of functions such as uniform for a given data set. So now let us say we can find the best fitting Gaussian and we can find the best fitting uniform distribution on the same sample. Between these two, which one is better? So a simple answer is that we just compare the likelihood. So if we take the likelihood of p, let us say Gaussian, right, so let us talk n, okay, this is the normal distribution of x and the parameters are mu star and sigma star, okay. If we take this and we compare it against the another distribution which could be, let us say, uniform distribution, and this distribution is again over semicolon xi semicolon, and here we have a and b, okay. So between these two, the one that gives us the higher value is going to be the better distribution, okay. We can also take log on both sides and compare the sum of logs of the probability. So the log likelihood is usually a better used formula, because when we take the product we can get increasingly lower values and they all multiply and they fall below the floating point limit of a computer. So we several times just use the log likelihood instead. So but given any data sample, so let us say we are given a few data samples, the actual best fitting distribution is something called the empirical distribution function. What is the empirical distribution function? That I basically put a Dirac delta function, okay, at every sample point and divided by n. So this is Dirac delta function, delta of x minus xi divided by n, okay. So what that means is that my cumulative distribution function will have these jumps of 1 by n, at each sample point, right. So this jump is always 1 by n. I didn't draw it very well, but all of these are 1 by n. So it starts at 0 at the minimum and it reaches 1 at the maximum. So the problem with just using the empirical distribution function as an estimate of all the other points is because we assume that the samples were actually drawn from an underlying, not a discrete like a probability mass function kind of thing, but from a continuous distribution, just that we didn't have sufficient samples to sample from the gaps between the two jumps. So these samples did not appear just because we had a finite number of samples. So if we take the empirical distribution function, it will fit perfectly on the training data, but it will not explain the gaps between the training data, and that is very crucial. That's why empirical distribution function is not very useful. What is more useful is to approximate this empirical distribution function. So let's say if this is the cumulative distribution function of the empirical data, then we want to approximate it using some smooth curve. So this is some smooth curve that also goes from 0 to 1, and that smooth curve will be different for uniform distribution. For uniform distribution it is going to be a ramp. For Gaussian distribution curve it will be a smooth S-shaped curve, etc. So we are trying to use a good approximation to this step type function, okay, and that will basically explain all the missing points also. And if we want to be more rigorous about it, we can also do something like so if we take the empirical distribution function but we fit it only on a subset of samples, it will give 0 probability on the samples on which we did not fit it, whereas a Gaussian distribution or a uniform distribution will probably still be able to give some probability, some likelihood on the points on which it was not fit. We held it out just as a validation. So that is also something that we can do to compare two different distributions. One way to find a goodness of a particular distribution is to do something called a QQ plot. QQ plot means quantile plot. So we take the x-axis and we look at the quantiles of an actual distribution, of a theoretical distribution, sorry, and then we look at the quantiles of the actual distribution of the data and we see whether they form a straight line or not. So what that means is, let's say we are looking at 1 percentile, okay, 2 percentile, okay, and all the way up to 99th percentile, okay, and then we form a table, okay. So this is theoretical Gaussian, and this would be, let's say, sorry, it will be the header here. So this is theoretical Gaussian and this is practical data point, okay. So let's say this gives us a value of minus 3.6, minus 3.2, etc., and this gives us a value of 2.4. Or standard normal Gaussian would be symmetric, then let's say it's something like 3.6, okay. And here we plot the actual values from the data. So if we have 1,000,000 data points, we can find this would be the 10,000th data point, and that is, let's say, minus 3.4, minus 3.1, and then let's say here it only reaches up to 2.7, right. So if we plot these two, we'll get some kind of a plot, and if that plot is on a 45-degree line, then there's a perfect fit. If the line is slightly changed, it is not at 45 degree, it is sloping, or its intercept is not at 0, then that the only thing that means is that the practical distribution is a normal distribution, except that it doesn't have a 0 mean and it doesn't have a unit variance. That could be the difference between the two. So that's all that we need to do to make sure that it looks like. So this is one of the visualization techniques to see whether it is a good fit for a Gaussian distribution. And this need not be just Gaussian distribution, we can replace this with exponential distribution, we can replace this with the Weibull distribution, etc. Okay. So that is another way of visualizing the difference between two different distributions, and the more rigorous way is to actually look at the likelihood of the data sample. Now what if your data is multimodal? So what that means is, let's say you have the x-axis, and on this axis you have a bunch of points that are bunched up here, and then it is becomes sparse, and then again we get another set of dense points. Okay. So the distribution here looks like it has some peak here, then it goes down, and then it has another peak here. So there is a very useful density function, it is still parametric, which is called mixture of Gaussians. So basically what it does is that it basically models the data as sum of multiple weighted Gaussians. So there is one Gaussian here, and then there is another Gaussian here, and basically we sum up the two Gaussians. So basically your probability of x is being modeled as sum over some set of Gaussians, and let's say there are k Gaussians, k is equal to 1 to capital K, okay, and within each we have a weight alpha k. So some of these can be higher, some of these can be lower, but each of them individually integrates to 1, and totally they should all integrate to 1. So alpha k, and then we have normal distribution of xi, okay, so let's say this is xi, okay, given the mu k and let's say the sigma or ck, alright, and the constraint is that all alpha k is greater than equal to 0 and sum over k of alpha k is equal to 1. So because each Gaussian itself integrates to 1, their sum should also integrate to 1, only then this is a probability density function, and for their sum to integrate to 1, we need the weight to be weights to be non-negative, and we need them to add up to 1. So what is this k? This k is basically a hyperparameter, and the mu k, the ck and the alpha k are the parameters which we will call theta. Okay, so this is the underlying assumption. Here it is not so straightforward to find what are the different alpha k's. It's not easy to find what are the different mu k's and what are the different ck's. So those have to be found using an algorithm which is not as straightforward as taking the sample mean or the sample covariance that we saw in the case of a single Gaussian. Now we have a mixture of Gaussians. So the algorithm that is used here is something called expectation maximization algorithm, and the way it works is the following. So we assume that there is some sort of a membership of each sample point to each of the Gaussians. So that membership is Wik, okay, and that membership adds up to 1. So if it is relatively more explained by one Gaussian, the weight will be larger. If it is towards the tail end of the second Gaussian, it will be the weight for the second Gaussian will be smaller, but they will all add up to 1. So the way they add up to 1 is that we will take in the numerator we will take alpha k, okay, so this is your Wik. So what is Wik? The weight or the membership of the ith data point to the kth Gaussian. So this is going to be alpha k, and then we will take the Gaussian probability P of xik. What is P of xik? It is basically the normal distribution of xi given mu k and sigma k. Okay, but now this will be divided by all such terms. So in the new denominator you will have instead of j I will take instead of k I will take j, but it is basically the same variable. So and now we will have alpha j, okay, p j xi, okay, and j runs from 1 to capital K. Okay, so this is the weight, and the weight for each sample adds up to 1. So so basically we will iterate over a few iterations, and we will stop when there is not sufficient change in, let's say, WIK. So let's see that there are parallels to k-means algorithm in some sense. So basically what we will do, or fuzzy c-means for example. So in the E step we will compute the memberships, and in the M step, in the maximization step, we will maximize the likelihood of the data given the weights. So we will keep the weights fixed, but we will find the maximum likelihood estimate of theta keeping the weights fixed. So what that means, that alpha will be the fuzzy membership divided by the total number of samples. So what is nk? Nk is sum of all the weights of all the samples for this particular k, and we will do this for all k. This will be for k is equal to 1 to k. Then the maximizing the mu that maximizes the likelihood is the weighted average of all the points weighted by the membership to that particular Gaussian. Okay. And then the ck for each class each Gaussian is going to be the average over all these points, but of the covariance. So it's going to be xi minus mu k and xi minus mu k transpose, but then it will be again weighted by wik. Okay, so this, if we iterate over this, we will be able to find the alphas and the mu's and the ck's for the mixture of Gaussians. Now let's go back a bit to the model, and let's see the parallels between mixture of Gaussian models and k-means and fuzzy c-means. So here what you can see is that the number of samples that are in one particular k-means or fuzzy c-means cluster, those are represented by alpha k. So that is basically the weight of that particular cluster. In this particular case, it's the weight of that particular Gaussian. And then the centroid is mu k, and in fuzzy c-means and k-means we assume that the covariance matrix is a scalar multiple of identity matrix. The data is isotopically distributed, and we also assume that all the covariance matrices are equal. Here we don't assume that. Here all the Gaussians are allowed to have different covariance matrices and skewed not skewed, but covariance matrices that are not axis aligned, they can be tilted, for example. But then when we look at the estimate, the learning algorithm for k-means and EM algorithm, there are parallels here. The parallel here is, for example, here we have in k-means we would have measured the cluster membership, and then we would have simply updated the centroids of the clusters. So similarly here we are measuring the fuzzy membership in some sense to each Gaussian based on how likely it is to belong to that Gaussian relative to other Gaussians, other of the k Gaussians, not like any Gaussian, other of the k Gaussians in the mixture. And then we are looking at what is the maximum likelihood estimate of the mu and the sigma for each Gaussian, and for the alpha of each Gaussian, or the weight of each Gaussian. So think about it this way, let's say we have a bunch of points, and this is a multimodal Gaussian distribution, right? So this looks like it comes from two different modes. So we can randomly initialize some mu k here, some mu k here, and some sigma k here, and some sigma k here, not sigma k, ck. Okay, and we can say that here alpha is equal to half, here alpha is equal to half. Okay, so both are equally likely. Now what we can see is that these points are more likely with respect to this Gaussian, these points are more likely with respect to this Gaussian, these are less likely with respect to the other Gaussian, and these are less likely with respect to the other Gaussian. So wherever you see dotted lines, the weights will be smaller, where you see solid lines, the weights will be relatively larger. So once we do that, when we compute the mu k, the contribution of the larger weights will be more. So hopefully in the next iteration, the mu1 will shift here and the mu2 will shift here, and the relative contribution, the relative number of points in the vicinity will also change the alpha k. So the alpha of this will become larger because it is explaining more points, the alpha of this will become smaller because it is explaining fewer points, and the ck or the covariance matrix will also tilt. Okay, it will have the required skews to explain based on what is the covariance of this particular sub Gaussian or the Gaussian in the mixture and this particular Gaussian in the mixture. So the eigenvalues and the eigenvectors will adjust to explain those, and within a few iterations we will have basically this kind of the final distribution will be something like a multimodal distribution. So now let us say if we do not want to fit a parametric distribution, we do not know what is the family of distributions that is more likely to explain this data, we also have a choice of something called non-parametric density estimation. The easiest method for this is something called kernel density estimation or Parsons window method. So basically the distribution of the data is going to be like this. If we have an unknown point px, it will be represented by a weighted sum of some kernel of x minus xi, and it will be divided by n. N is the number of samples, so I is equal to 1 to n. What does this mean? So let us say this is a Gaussian kernel, each kernel by itself integrates to 1. So when we add n such kernels, we have to divide by n. So basically what we are saying is that we have bunch of xi given to us, these are your training samples. On each of these xi, we will fit a Gaussian distribution, and the Gaussian distribution will be exactly the same for all of these. So you can see somewhere there are less overlap, somewhere there is larger overlap. Whenever you have larger overlap, when we add these up, we will have something that follows this, and then we will have something like this where the peak is slightly larger. So whenever we have more density of points, we will have larger peaks, okay, because their Gaussians will overlap with each other and they will go up in the estimate. This need not be just Gaussian, it can be a triangular kernel also. So triangular kernel would look like this, and we would add multiple of these kernels depending on whether the underlying points are closer or further apart from each other. So there are different choices, but Gaussian window is one of the most likely, most widely used ones. So now the overall distribution is like a mixture of Gaussians, where the mixture has n components, right, but they all have the same sigma and only varying mu. The mu is sitting on top of xi, okay, the sigma is the same, and sigma is something like a hyperparameter. So I can say that there is a hyperparameter here sigma, or h, I will call it h, the width of the window h, and that is what we need to estimate. Because if we have too narrow of a window, then we will have distributions that just look like this, which does not look very smooth. If we have too large of a window, then we will just get this. What we want to get is something that is representative of multiple modes and high densities and low densities. So what we want is something that looks like this when there are a bunch of points here and bunch of points here. Okay, so the sigma of, or the width of the kernel the hyperparameter, that is quite important to estimate, and there are some heuristics to estimate that window. Let us look at what those heuristics are. So basically the finding the optimal window size means that we want to minimize the mean square error between the cumulative distributions of the empirical data distribution and the Parsons window or the estimated distribution that we have. So let us say we have P empirical and we have P estimated. So P non-parametric. Okay, if we integrate both of these, so let us call it, we will integrate it to capital X, let us say. We take their difference and then we take their squared, we take that expected value, okay. That is basically, so this is from minus infinity, that is what we want to minimize, okay. So for Gaussian distribution, sorry, not for Gaussian distribution, for Gaussian kernels, it turns out that a heuristic is that we take the sample covariance, okay, and the number of points, and we raise the number of points to the fifth root, and we multiply it with the sample covariance. A better estimate is that we can also use the minimum of the sample covariance and interquartile range. So this is the difference between 75th and 25th percentile of data. Okay. This is all for one dimensional functions. So we take that interquartile range and we divide it by this 1.34 and we take the minimum of the two and then we take this. So the reason this one is used sometimes than the other one is because it takes into account if the data is skewed, the distribution is skewed, it is not symmetric around the mean, then we can take this interquartile range and it gives better estimate than the other one, just based on the sigma. And basically these are derived by trying to optimize what I have shown above. Now here the optimal window size and the optimal kernel density, these are all based on the assumption that we are looking at a single dimensional Gaussian, but the technique is useful enough even for multiple dimensions. So if we have dimension x1 and dimension x2, we could have a bunch of points, okay, and on each of these points we could actually put a Gaussian kernel, divide each of the kernels by n, capital N, and then add it up. Basically we will get a probability density estimation of the given sample point. Now here we have a choice of actually using a isotropic kernel or an anisotropic kernel, and there are other techniques to estimate whether to use isotropic or anisotropic kernel based on the skew in the overall data itself. So if the overall data is skewed, it is correlated and it is along some line, then the kernel itself can be tilted along that line and so forth. So once we have a density estimation, then the question is how do we generate a sample from a particular distribution. Okay. So generating samples from a distribution itself is quite an interesting field. So first of all, why would we want to generate a sample? So many times what we want to do is we want to augment the data, we want to increase the number of samples that we have. For that we want to increase we want to generate realistic looking samples. We could also want to not use the original training samples because they are copyrighted, so we want to generate new fake samples. We want to generate fake samples to test the boundary robustness of classifiers, that how close are classifiers to a particular decision boundary, etc. And another reason could be that we want to approximate some expectations. So if I want to find a function expected value of function x, f of x, right? So the actual formula for this is that I will integrate from minus infinity to infinity, okay, or let's say x is even multivariate, so I don't, it will be like multiple integrals. All what I want to do is I want to estimate fx px dx. Okay. So I will integrate this over px and dx. Now the problem is that this integration is quite costly for several types of distributions. Either it is costly or the underlying distribution may not be known. Okay. So let's take the example of when the distribution is known but the integration is not analytically doable. In that case what we will do, or let's say if f of x itself is only at some point estimates, then we can approximate this as a sum. Okay, and that sum, as you can rightly guess, is going to be over 1 over n, and basically what we want to do is we want to do f of x and yeah, so basically we can take the sum and then we can take the probability of x in that case, or sorry simply the average of f of x. So here the assumption is that the x is generated where x is sampled from p of x, is sampled from p of x. So what does that mean? What that means is that that if x, so let's take a value x star, right, or x, so let's draw this out. So let's say this is p of x. If I draw x from p of x, I will get a lot of samples that will be closer to the mode, and then I will get fewer samples where the likelihood is less. Okay. So if it is a smooth function, now let's draw f of x, it could be any function, it could be any function, right. So if I take more and more samples from here of f of x, and these need not be like on the same scale even, and fewer samples from here, then in some sense I have taken a weight. So what is the likelihood of a sample appearing here? That is, the weight is going to be proportional to p of x. So naturally I am taking some sort of a weighted average if I sample x from p of x and then simply sum the function based on that. Okay. So that's how I can approximate the function, the integral of that function or the expectation of that function using a Monte Carlo simulation, basically by generating samples from x. Where is this useful? Many times we want to take, for example, mutual information of two variables and so forth, where we want to find the expectation of the two variables appearing together and so forth. So how do we generate this sample? If the cumulative distribution function is simple, and I'll tell you what simple means in a bit, then the procedure is simple, straightforward. We generate a pseudo random number from a uniform distribution, from standard uniform distribution u of x, and then we transform the uniform distribution to the cumulative distribution function of that, the target distribution. So let's say we want to generate a function, so let's call it p instead of f, let's call it p, capital P, and this is capital P. So what is capital P? Capital P is nothing but this is the integral of the small p from minus infinity to x, so that is capital X. So this is the cumulative distribution function. So if we can take the inverse of the cumulative distribution function p, okay, that's all we need to do for samples generated from a uniform distribution. Why does this work? Okay, so take an example of a cumulative distribution function. So let's say a Gaussian cumulative distribution function. It will start from 0 and it will slowly rise up to 1. So it will go from 0 to 1. Alright. Now imagine that that we want to sample from this distribution such that we get more and more samples from wherever the density is higher, which means the slope is large, and fewer samples from the places where the density is smaller, which means the slope of this PDF is smaller, because density is the derivative of cumulative distribution function. So here all we need to do is, if we take the inverse of this function, we know that it will go from 0 to 1, and so basically if we take this uniform distribution function, standard uniform that goes from 0 to 1 and rises from 0 to 1, if we take the inverse of that, we will be sampling from the distribution small p whose integral is capital P. But this assumes that you can compute the CDF and you can compute the inverse of the CDF. Okay. So that is a tall order it's not possible for all kinds of distribution, it's very difficult for all kinds of distributions. So this is only useful for standard distributions such as the normal distribution or the exponential distribution, where we know P, we can convert from P to capital P and we can take the inverse of that. If we have multivariate distributions, one way to do that would be, let's say if we have P of xy, right, if it is factorizable to P of x times P of y, then we can simply generate samples from P of x using the CDF type approach, and generate samples from P of y using that CDF type approach, and we can multiply the two, and that will give us a joint probability. But not all distributions are factorizable. Factorizable means that the two data dimensions are independent of each other. In a Gaussian, that would mean that the Gaussian is always axis aligned, and we cannot make use of tilted Gaussian. So this one, for this this may not work very well. So basically in such cases we can sample from a proposal distribution and filter, and that is what we will look at for the next few minutes. So the first way to sample from a particular distribution is rejection sampling, and here we assume that computing P of z or P of x is easy. So what that means is that, let's say I have a distribution, right, and let's say the distribution is some complicated distribution, that given any point z, so let's say this is z1 and this is z2. Okay, so if I take a point z, let's change the color. If I take a point z, then I can compute P of z, right, but that does not guarantee that I can generate samples from P of z. Generating samples requires, so for example here if I want to generate samples, I may want to use a separate distribution. I can easily generate samples from an axis aligned Gaussian based on the factorized distribution. So I can have some q of z1 and some q of z2. So these are proposal distribution. This is called a proposal distribution. Okay, and let's say this can be factorized, and it can be factorized into standard forms such as Gaussian distributions. So I can generate from one dimensional Gaussian P of z1, sorry, q of z1, and another one dimensional Gaussian q of z2, and let's say I can multiply the two to get q of z. Now using q of z, how will I generate samples from P of z? So, and P of z, mind you, is a complicated distribution for which I cannot easily generate samples, but I can compute, given a z value, what is P of z. So let's say this, so basically in rejection sampling what we will do, we will first generate a sample from q of z, okay, and then we will accept it with probability P of z divided by k of q of z, k times q of z. So what is k? K is a constant such that k of q of z is greater than or equal to P of z for all z. Okay. So if that is the case, I have to find a particular k where q of z will be greater than equal to all p of z. So now think of it this way. Now if I draw this in one dimension, right, so you have some complicated distribution, and we have, so this complicated distribution is p of z, okay. So this is z, and the other thing is the other axis is the probability, and I take q of z, which is a simple distribution, and I increase its height to the extent by multiplying with k, so that it is always above p of z. So this is q of z, k q of z. Now once I sample from p of z, I have this much probability of sampling it, or something proportional to this, but I will accept it only when in this proportion, which is the proportion of p of z, and I will reject those that are above that. So ultimately that means I will be sampling from p of z. Okay. The disadvantage of this is that there are, wherever this ratio is small, right, p of z is much smaller than k q of z, then I will reject a lot of samples in that region, and I will be generating a lot of, I will be wasting samples in those regions. Plus the other disadvantage is that I have to find a good value for k, otherwise this scheme will not work. On the other hand, there is another strategy where we do not reject there is a second strategy where we do not reject any sample. We accept all samples except that we assign them weights. So where this is useful is, let's say we are trying to integrate, we are trying to find the expected value of f of z, which is f of z times p of z. Okay. Instead of that, what we will do is we will sample z from qz, which is easy to sample from, right. So we will have sum of f of z, okay, but we will also have w of z, some weight w of z, okay, and where z is sampled from not p of z, because that is difficult, it is sampled from q of z. So this symbol means z is sampled from q of z, okay. So it will help us do this integration, and this weight is now the ratio, so that we know that from Monte Carlo, if it was sampled from z, then basically this would have been, if we did not have the weight, this would have been integration over q of z. Now we are replacing that q of z by actually taking the ratio of p of z to q of z, so that it actually becomes integration over p of z. So this is the importance weight, importance of a sample, importance of sample z, okay. So that is why it is called importance sampling. So there is no rejection, no samples rejected. It is another matter that it suffers from the same problem, that we may have a lot of very small weights, because the ratio of p of z and q of z are different. So in both these cases, in rejection sampling and importance sampling, what is to be kept in mind is that q of z should be a good replica of p of z, otherwise it will either reject a lot of samples, or it will drive a lot of sample weights to 0. So that should not happen. For both of these cases, if we do not find a good replica of p of z and q of z, then we will get inefficient sampling. So if we do not find a good q of z, there are other ways of sampling from p of z by constructing something called a Markov chain. So what we saw before this, that all the samples that were sampled, all the z samples that were generated from q of z, they were independent of each other, they were IID, independently and identically distributed. Whereas in Markov chain Monte Carlo, the sample that will be generated will be based on the previous sample. It will have a conditional distribution over the previous sample. So basically when you generate a sample, the next sample will be likely to be close to it, and if we want to sample from a distant part of the space, then only when the chain actually goes in steps and reaches that part, only then we will be able to generate the sample from that other part of the state. So these will all be, so there will be a Markov chain, and the chain will be slowly moving in the space, and if the chain is long enough, then if we take all the samples and we shuffle them, they will look like as if they are IID, but if we just look at the sequence in which they are generated, they will not be IID. So basically what we are trying to do is the following. So let's say we have a complex distribution and it is spread out like this. So these are the contours of equal probability in Z1 and Z2 space. Okay. So what we are trying to do is trying to generate a random sample, and then we are trying to generate other samples close to it, okay, and slowly generate a lot of samples, so all these are in a sequence, so you will see a line through them, and we are slowly trying to generate a lot of samples so that it explores everything in the large space. So when we generate each of these samples, these contours of conditional distributions will be small. Okay, so we are only exploring a small neighborhood, and this could be an isotropic Gaussian, for example. We are taking a small step in the nearby neighborhood, but the probability of accepting that step would be based on the relative distribution of the initial point versus the next point. Okay, so that's what we are looking at, and overall when we take, let's say, 1,000,000 samples, then hopefully we have explored everything in the original distribution P of Z. Right. So again, P of Z is easy to compute, but it is not easy to sample from. That is the assumption. So here the other advantage is that now this Q of Z need not be a good replica of P of Z. It is only a good replica of the neighborhood in some sense, or it doesn't even need to be like that. It just needs to be exploratory enough in the neighborhood. So so here we will iterate over the number of samples T. Okay, so that will form a chain. T is equal to 1, T is equal to 2, so T is equal to 1, 2, etc. Then we will reach T and then T plus 1. Okay, so we are generating a lot of samples. So when we iterate over T, whatever was the last sample in the chain, right? So your chain is like this. Okay. So this is the chain, and so let's say this is T and the next one is T plus 1. Okay. So what we are going to do is we are going to generate a sample from QZ given ZT. So whatever is T, we will take an isotropic Gaussian and we will sample from that distribution. We will get some Z. Now we will either accept this Z or we will reject this Z with some probability. The probability of acceptance is a minimum between 1, right, because it cannot be greater than 1, and a ratio of two things. The ratio is that of P of Z divided by P of ZT, and the inverse of P of ZT given Z and Q of ZT given Z and Q of Z given ZT. Okay. So basically what this means is that so actually we wouldn't need this, we wouldn't have needed these two terms if this was symmetric. If these are symmetric, then we wouldn't have needed those terms, these would have cancelled out. Essentially what we are saying is the following, that from a low density region, relatively low density region, if the exploration step, right, the generated sample. So if you have ZT, and so this is ZT, and let's say this is Z. So if the relative density of Z is greater than that of ZT, then surely accept ZT, then take that step, otherwise stay at ZT. Okay. So either stay at Z, either go to Z or stay at ZT. So we surely accept if basically P of Z is going to be P of Z is going to be greater than P of ZT, and if it is less, then we might reject that sample. Okay. So we will reject it with the probability P of Z divided by P of ZT. The other thing, these two terms are only to account for the fact if the jumps were not symmetric, so usually they are not even used. So essentially if we use the terms, it is called metropolis algorithm, and if we use a non-symmetric Markov chain, then it is metropolis Hastings algorithm. Okay, so in metropolis algorithm we will just have min of 1 comma P of Z divided by P of ZT. So where you are coming from, so you are more likely to go to places where the probability is higher. That's all it means. Alright. So imagine if you had a chain that was way out somewhere in the low probability region. It started there because our first sample was randomly generated. So here it will spend a lot of time, the chain will meander in the low probability region before it gets here and it starts to explore the high probability region. So usually the first several samples of the chains are rejected, that's called the burn-in period. After that we can accept the chain, and we can also have multiple chains running so that we, so let's say if it is a multimodal distribution and the other mode is very far away, if we explore only this region but this chain never escapes to the other mode, that there is a probability of that. So we actually can have multiple chains, and then we can take all the chains, the samples generated by all the chains, shuffle the samples, and we have a good IID kind of looking sample from the particular distribution. The last topic that we will talk about in generating samples is Gibbs sampling. Here this works well when we have conditional distributions, that is we are able to generate the ith dimension given all but the ith dimension. So this notation \i means all the dimensions of Z except for the ith dimension. So if we have, so for example let's say we have 3 dimensional, okay, Z1, Z2 and Z3. So if we can generate samples from P of Z1 given Z2, Z3, and we can generate samples from P of Z2 given Z1, Z3, and we can generate samples from P of Z3 given Z1 and Z2. Okay. If we can do that, if we have these 3 conditional distributions, then we can use Gibbs sampling. So what we would do is that we would iterate over the number of samples, we would iterate over dimensions, this is not samples, this is dimensions, and we would generate the ith dimension of the t plus 1th iteration, okay, by using the conditional distribution of the ith sample with all ith dimension given all but the ith dimension. Okay. And this itself can be done, let's say using metropolis like a rejection sampling or some of the other sampling methods that we have talked about before. So this gives you some idea about how samples can be generated, how distributions can be estimated using a parametric and a non-parametric form, and how we can use it for finding expected values of certain functions in machine learning. Thank you.